So with the microphone now, we are welcoming Sara Rebecca Gozzini for this second colloquium of the year 2026. She's a researcher at the Institute for Particle Physics in Valencia. And in addition to her former life as a cosmic ray and gamma physicist, she's been working on neutrinos in the IceCube and KM3NeT collaborations, which is, I believe, what she's going to talk about today, pitch dark underwater.
Yeah, thanks very much. Thank you. I'm very happy to be here, and I wish to thank Felipe and Ignazio for inviting me over. So I'm a member of the KM3NeT collaboration, and I will be giving an overview of how neutrinos are actually detected in KM3NeT and actually enter the landscape of multi-messenger astronomy and other physics cases. So first of all, I like to start by setting a little bit of a forward that the cosmos does actually work very well as a particle lab at extreme energies and or very large distances, especially when one considers what undergoes the name of Higgs and nothing else, in the sense that after the Higgs discovery, when it comes to big breakthroughs, colliders have devoted like a targeted discovery case for Higgs, a high exposure, or let me say precision measurement for the measurement of all Higgs couplings, and then some B-meson anomalies, CP violation in baryon decays, tetra and pentaquarks. But on the other side, we have the cosmos when we have similarly targeted discovery, gravitational wave, missing for about 100 years, ever since its theorization by Einstein, and finally caught in the last decade. Then there is this sort of expected or semi-granted measurements, such as neutrino point sources, which is a matter of having a large exposure, so waiting enough time, being enough lucky with transients. But also plenty of serendipitous discoveries. So discoveries that weren't expected at all, such as the CMB, which Penzias and Wilson were like playing radio amateurs and fighting very long to get rid of this kind of background that turned out to be one of the breakthrough discoveries of the century. Neutrino oscillations that were indeed first measured with precisions in detectors that were born to measure proton decay, for instance, and many more. So what I want to bring up is that Cosmos actually works as a particle lab, and not just lately, but there was plenty of discoveries. So the lower part of this triangle is earthbound, or let's say collider, accelerator discoveries, and the upper part is whatever was discovered in the cosmos, and there is plenty through the years, starting from the observation of cosmic rays that were actually discovered in astrophysical environment. And also that astroparticle comes as in the list of the many breakthroughs of the last decades, with listing just a few of the main discoveries that characterized the latest years, starting from Higgs to the first measure of astrophysical neutrinos, gravitational waves, the neutrino mass Nobel Prize, which is very recent, although observations were more than 20 years old. First multi-messengers observation of neutrino sources, the kilonova 2017, so correlation of gravitational wave with gamma ray burst, which gives an idea that actually astroparticle physics deals with very small number of events, sometimes even one, so a single event, and so on. So let me introduce now the main milestones of neutrino astronomy. Neutrino astronomy actually can be dated back to 87, when about a handful of 24, 30 neutrinos were measured as predecessors of the arrival of optical light from the supernova 1987A, which is actually the first object to be mapped in neutrinos. It's actually in the Magellanic Cloud, so it's an orbiting like at the edge of the galaxy, so slightly extragalactic. And then I'm showing you here the one picture on the left. This is an historical picture, 99. This is the image of the sun they mapped with neutrinos by Kamiokande. So this is actually what we mean by proper astronomy, so backtracking or description of the source using a messenger. Then major breakthrough, 2017, published 2018, is the first multi-messenger source measured by IceCube, and I will present a very recent result by KM3NeT too. But the main thing here is that to say that neutrino astronomy is a science of extremely small signals due to the typical neutrino interaction rates, which require a very large instrumented volume, which means a very, very large background rate from cosmic particles which are daughters of no neutrinos, such as typically muons, so very abundant. So this is a science of doing statistics of extremely small signals over a very, very large background. Right, and this brings in the fact that actually is not just astronomy, it's multi-messenger time domain astronomy. In the sense that particle physics and astronomy are now entirely, let's say, bordering and incorporated into one another, into astroparticle. But what we call astroparticle or particle astronomy is no longer static astronomy, so picture or let's say aimed at the description of the object one points at. But it's actually a dynamic astronomy, so time domain, which bases on flare, explosions, turbulent and transient phenomena. And it's also devoted not just to the inspection of the morphological properties of the object, but as well to the physical processes that lead to the emission. And what do I mean by flares is a situation like this. This is, for example, the view caught by the Fermi satellite. And you can very well see that on top of a quiescent emission, this is over a large number of years, you can see the counter on the top left. On top of the quiescent emission, there is a number of very variable and very various turbulent phenomena appearing, and we name those as flares. And flares is actually one of the smoking guns for astroparticle, for particle astronomy. Right, so then when we talk about astrophysical messengers, of course, those messengers travel extremely long distances between impinging into detectors. That means that they give the opportunities to study extremely low flux phenomena that scale, for instance, up with energy or accumulate over distance, but they undergo some problems. For instance, photons typically can be lost by pair production when photon impinges on a target photon, and there's plenty of these target photons in cosmic environment. There's light from stars. There is, for instance, infrared emission from dust. But then ultimately, there is the CMB. And CMB is very low energy, but everywhere. So the higher the energy of the incoming photon or gamma ray to this point, the higher the chance that at some point this photon goes lost to a pair production. So this fixes some sort of horizon for the observation of very high energy photons. On the other side, there's cosmic rays. So cosmic rays, I mean proton, nuclei, anything charged. So they're normally deflected. The deflection is proportional to their rigidity, to their charge. But the charge is event by event unknown. It is actually studied on a statistical mixture, but it's impossible to ascribe to a single event. And then finally, there's neutrinos. They don't go any better than others because neutrinos don't even interact with the detector directly. All human-built detectors are electromagnetic, no other chance. So neutrinos go detected through their daughter particle, which is a charged lepton, typically muon or electrotau, and this guy can, at relativistic energies, emit photons in a Cherenkov, enveloped in a Cherenkov cone, which is the way we do detect neutrinos with large volume telescopes. That is, the chance for neutrino interacting and issuing such a lepton goes to the weak interaction to very low rates, and that is why we need to instrument, indeed, very large volumes. So this is pretty much the same situation summarized. Moreover, there is the problem that even for gamma ray imaging, Cherenkov imaging detectors, such as the case, for instance, for MAGIC, Hess, CTA, Veritas. So the reconstruction goes indirectly, as these detectors work really as cameras, like reflex cameras with mirror and pointing, focusing on a shower initiated by a gamma ray very high up in the atmosphere, so 20 kilometers and more. So they have indeed to reconstruct the incoming gamma ray starting from that. Then there is the double uncertainty for cosmic rays, detection and deflection due to composition, and the indirect case for neutrinos. But once assessed this, I will now spend a minute to imply that particle astronomy is particle physics to all respects, in which when we are considering the case of an accelerated, for instance, proton, as in the case here in the left, dragged along in a supernova remnant expansion front, and then scattering onto a target, for instance, of molecular material like a nearby molecular cloud, then producing neutrinos. This is exactly identical, analogous to what happens in beam-down experiments, where proton is accelerator, hits the target, and then produces neutrinos in the final state. So this is exactly the same physics process, just at two very different energy ranges. And there is a strong connection between neutrinos and gamma rays and cosmic rays when it comes to hadron acceleration. Because all sites where proton or nuclei are actually accelerated to high energy, they radiate neutrinos and photons, most likely simultaneously. I'll mention an exception right now. So this can happen either for proton or nuclei, like in the case I just showed of a supernova remnant surrounded by molecular material. Or it can happen despite the cross-section for the second process is actually 5 orders of magnitude lower, but it can happen that photons scatter on gammas, if gammas are dense enough. And in astrophysical environment, there are cases that present a very high density for radiation. This is the case of jets in active galactic nuclei, for example. And in the first or the other case, both charge, for instance, and neutral pions are produced, and therefore both photons and neutrinos at very high energies are produced. So this suggests a very strong connection between hadronic acceleration and neutrinos and gamma simultaneous emission. Moreover, flares and transients, so the observation of sources with a very high variability, actually matches a very suggestive scenario of having a quiescent emission underlying and say constant, explained with the leptonic emission, so the emission of gamma rays, for instance, due to accelerated leptons, electrons, for instance, on top of which a blob, for instance, of accelerated proton crosses regions with high density of photons and emits photons and neutrinos. That would exactly create the phenomenology that we observed, that sources are seen in a quiescent and lower intensity state, and then suddenly they flare to a higher intensity. The duration of this flare, for which there is no, let's say, classification to the time being, can be actually related in this scenario to the size of an accelerated blob dragging along the accelerated protons. That suggests a prompt alerting system in order to perform a rapid cross observation of neutrinos and gamma rays. So the entire astroparticle multi-messenger astronomy is based on this. So we said that, okay, leptonic acceleration and radiation issues no neutrinos, hadronic acceleration issues neutrinos and gammas. Does that always imply that neutrinos and gamma are emitted in parallel? Alas, yes and no, in the sense that they are emitted, but in some cases gammas are obscured, in which they're captured by the environment of the source itself. And this was, for instance, the case for NGC 1068, which is the first static neutrino source observed in neutrinos without electromagnetic counterpart. Right, when it comes to resolution, because now I will move to neutrino telescopes, but I want to put it a little bit in context with other experiments. So cosmic rays observatories such as Auger, they actually can come to a relatively nice sub-degree resolution, especially when going to hybrid events, so events that consist of data taken by a ground Cherenkov array, combined with the fluorescence telescopes at the side. And they observe a field of view that, okay, classically speaking, it could be 2 pi, but it's actually normally, yeah, it's about 60 degree, not 90 degree opening. So normally it's very difficult to measure extremely inclined event. So they can have a pi radians field of view. Gamma ray instrument, they cover a very broad kind of energy spectrum. They go from calorimeters such as Fermi, they go to Cherenkov imaging, and to very large arrays such as Hawk and LASO, for instance. So the calorimeters such as Fermi, they have an excellent energy resolution. However, this instrument flies, so it's limited in volume, so the gamma collection area is forcedly limited. But Fermi, for instance, scans the entire sky, I believe 4 times a day. So 6 hours, a complete tour. Then there is to the higher energy shifts, so up to TeV region. So up to 100 TeV, there is typically gamma imaging Cherenkov telescopes. They can have a field of view of about, so it's a small field of view, so it can go like 3-5 degree square in the sky. This is a very little field of view, which means that they have to point, and somehow they have to divide the observation hours according to the importance of the coordinates of the sky they wish to observe. They come to a very excellent angular resolution, so sub-decimal of degree, but indeed they undergo this problem of source booking. And then there is the very large arrays, and also Cherenkov imaging instruments, they are confined, they are restricted to observations in perfectly dark nights. They cannot observe during the day, they cannot observe with full moon, and these kind of things. And then to the even higher energies, there is ground arrays that can come as well to a very good angular resolution. They have a modest energy resolution, but then they operate to a very high duty cycle. And now we come to neutrino telescopes. The neutrino telescope, they work at very faint rates, which means they can actually, but they have a very high uptime. So it's technically 100%. So they take data continuously. What we do is sometimes we stop the regular data taking for calibration, but apart this, they go on. And by default, they come with a 2 pi field of view, if not 4 pi. I'll explain this. So technically speaking, they need to filter out all kind of charged leptons, especially muons, which are very, very abundant. Interaction of cosmic rays in the atmosphere produce plenty of muons. And they need to filter those. So the way they filter those is they look across the Earth. So they use the Earth material as a screen, only neutrinos are able to cross. Then when such a muon is produced from something coming from below, this is for sure daughter of a neutrino interaction. Neutrinos come from everywhere, but discriminating the amount of neutrinos from above with respect to muons is technically impossible, also to the very large number. They come to a nice angular resolution. They can go as low as sub-degree. They're remotely operated, and also they don't point. So they got a unique data set that actually suits plenty of physics cases. And what I'm showing here is the case, for instance, for KM3NeT. They cover the energy between GeV up to PeV and above. So KM3NeT consists of 2 detectors that are currently in a construction phase. So those are arrays of photomultipliers in the seawater. They instrument the seawater using this as a detector medium to create Cherenkov effect. The property of these instruments is they have a modular layout. So they consist of strings, like cables, of a very strong material. It's called Dyneema, as a material also used in constructions, and is very resistant kind of cable. And as soon as a string is actually placed in the seawater, robotically it's connected to the data acquisition on the sea bottom, and it can start taking data. So it means that these instruments don't need to be complete to take data, but they can take data in partial configurations. So they're already taking data, both of them. So they consist of 2 different instruments that have exactly the same unit, the photomultipliers, but they have different geometry, different spacing, according to 2 different physics cases that they wish to address. So we have a very compact and dense module, which is called the KM3NeT ORCA. The O stands for oscillation, because this instrument wishes to use atmospheric neutrinos, so a copious amount to very high statistic of atmospheric neutrinos to measure oscillation parameters and to attempt the measurement of the neutrino mass ordering. So this guy is placed underwater to 2.5 kilometers, close to what used to be the site of the Antares telescope, which was also a prototypal neutrino telescope in the Mediterranean that is now being entirely removed. So, and then there is a future cubic kilometer, which is called KM3NeT ARCA, and the A stands for astrophysics. And this is placed at 3.5 kilometers on the sea bottom offshore the southern coast of Sicily. So to scale, they are displayed here. So ORCA, the small module, has a spacing of 23 times 9. And ARCA has a spacing of 90 times 36 meters. So between lines and between optical modules on the same line. And the picture here on the top right also illustrates the situation. So these guys are deployed just after the continental shelf in very obscure waters in order to filter out any possible other sort of light that might indeed disturb the measurement of the Cherenkov cone light. They are cabled to shore, and on the two shore stations close to Toulon, in La Seine, in France, and close to Capo Passero in Italy, all data are sent. So we don't filter any data at detector stage, we transmit all data because they undergo different processing chains. Those that serve for prompt multi-messenger astronomy, so alerting issues, must be processed in a rough and quick way, so within minutes, in order to be sent away to our partner instruments in networking. Those that go for a high-level data processing instead are stored and filtered with different criteria, but all data are sent to shore at once. So that's the collaboration. So KM3NeT is mostly European collaboration. It actually overlays a lot with what used to be the Antares collaboration. I think almost all members are coincident. It has strong contribution from Spain. It has major contribution as well from France and the Netherlands and Italy as well. And it currently counts 21 countries and 68 member institutes. And this graph pretty much gives an idea of what has been constructed until now. So the final stage of these two detectors will actually count 2 blocks of 115 lines each for ARCA, and it's a little bit less than 115, so 108 lines for ORCA. And in the current moment, there is 51 lines for ARCA and 33 lines for ORCA that have been deployed over the years. So events for us consist in these two topologies, so shower-like and track-like. Now I'll spend a word about this distinction that sounds clear, but track-like events are the easy ones. They come out of a charge current interaction of neutrino to muons. So muons typically cross the entirety of the detector in a sort of linear, leaving behind a sort of linear trace. Not entirely contained in the detector sometimes, depending on the energy. So their pointing resolution is excellent. Their energy resolution depends, because part of the light might be deposited outside the instrumented volume. Instead, we have cascades. Cascades can be hadronic or electromagnetic. So typically electromagnetic cascade, you can imagine an electron coming out of a neutrino, electron-neutrino to electron process. Electron loses its energy immediately to Bremsstrahlung, so it does some sort of a spherically shaped signature, which is typically entirely contained in the detector volume. That means that these kind of events have a perfect better energy resolution. It's more difficult to evaluate their arrival direction. Right. However, this said, this was the, let's say, theory or the good intention, but then you are left with events that might look like this one. So, especially to low energy, right? So, distinguishing tracks from showers is not as easy when you go to lower energies. So you can compute that a muon of 1 GeV, if you know how muon energy loss goes, so you can calculate the muon range given water properties. So the muon at 1 GeV travels about 4 meters. So a track, a muon with 1 GeV leaves a 4-meter track is very easily mistaken with a cascade, because the amount of hits, the amount of Cherenkov signals that our cameras can detect are little, and our modules are far apart. So at some point, this is what determines our threshold at GeV-ish, because events below these energies won't trigger with respect to spurious noise, which of course I forgot to mention, but we have in water, because we have potassium-40 radioactive decays, and we have bioluminescence, so light emitted by organisms in water, and we have electronic noise, of course. So spurious hits at some points will be indistinguishable from our signals. But indeed, they are particle classification, so the particle flavor discrimination, depending on the signal that it leaves behind, depends strongly on the energy. So if you talk astrophysics, you go at TeV and above, right? You're doing well enough with us with simple cuts, because distinguishing a track from a shower is some sort of more easy. If you go to low energy, however, you need to rely on boosted decision trees, because telling tracks from showers is not as easy as simple cuts. But here I have to mention that the specialty of KM3NeT, when you look at its optical module, so this is its unit, is actually equipped not with a single photomultiplier tube, as in the case, for instance, of Antares or IceCube, but is equipped with 31 smaller area, so it's 3 inches, is about 7-8 centimeter diameter photomultipliers that cover a larger effective area on the optical module itself, but also add some sort of possibility for precision in the angular reconstruction for arrival of photons at the photomultipliers. On top of this, there is the medium. I was naming it lenses for some sort of assonance. So water, for instance, with respect to ice, turns out to be an excellent optical medium, right? So you have the situation for ice on the left-hand side of this picture and the situation for water here. The two signatures are respect track and a cascade at 10 TeV, so very high energy. As you see, the signature is clear. But the more red the color means that the hit is direct. It means this photon hit the photomultiplier before undergoing the first scattering. Water has a larger scattering length than ice. So it means that almost all photons hitting our photomultipliers are direct. It helps a lot in reconstructing the arrival direction of the event, because we're more precise with that. Right, and then I just want indeed to mention that at some point, this is fundamental for what I'm gonna talk about, at some point, so neutrinos, I just said they cross everything, well, depends on the energy, at some point they start being absorbed as well. Indeed, they start somehow being absorbed by the Earth as well. So somehow when you wanna move to PeV and to EeV energy ranges, the amount of phase space that is left for you available becomes more shrinked due to this. Right, so very, very, very quick flash of what happens with neutrino sources. So astrophysical neutrinos, first of all, were detected by IceCube with these two cascades that were the first whispers, as they say in spy stories, so the first precursor signals that the diffuse component started to be close by to be hit. And indeed, the year later, IceCube published the first detection of an extraterrestrial flux, or astrophysical flux of neutrinos. This measurement was going nicely on with events nicely growing with time and the significance for this component increasing down to 2017. So that's ICRC, this is summer 2017, International Cosmic Ray Conference. Still no sources, however, so only a diffuse component. Diffuse means no arrival direction information whatsoever. In 2017 September, so just after, IceCube could, for the first time, detect a high energy event that per se wasn't particularly exceptional, was high energy, but not phenomenal. But it could be promptly correlated with the high state of an event, of a source underlying the event. So this source is named TXS0506 plus 056. It's an AGN underlying, and other telescopes, especially MAGIC and any other gamma ray and other messengers, could see the source in a high state. So they could correlate exactly what I was mentioning in the beginning, the correlation between neutrinos and high energy and photons in all wavelengths. So this permitted to identify this source as the plausible source of this high energy neutrino. There's more sources being detected ever since. This is as far as 2022 by the IceCube collaboration, especially also a static neutrino source that I was mentioning in the very beginning. So a source for which neutrinos are significant enough, indicating the origin with the galaxies NGC 1066 without any gamma counterpart. And then, as late as last year, KM3NeT measured this particularly high energy event. Maybe I can replay another time. Right, this is crossing from the side and from the top the 21 line configuration of our detector. Now, this event is spectacular because of the amount of triggered photomultipliers that were hit. So it's about 1/3 of the entire detector, a lot of light deposited. It crossed the detector in 2023 February. So it interests the configuration with 21 line of the detector. This event indeed was coming horizontally, exactly as expected, as I was saying before. It needed not be absorbed, so it was particularly lucky. So it's a serendipitous discovery that was not expected with as small as a detector, but still undeniably illuminated more than 1/3 of the entire detector. And undeniably is not an atmospheric muon because of the amount of material crossed would have blocked the muon. It's about more than 100, it's 100 kilometers, but also is water equivalent 300 kilometers because that's not only water. Even more luckily, it crosses from a direction that it actually meets rock. So it crosses the continental shelf from the direction of the Malta Island. So that's definitely not a muon from coming in this direction. So the energy of this neutrino event was estimated to 220 PeV, assuming a e⁻² astrophysical spectrum, coming from the data of a muon with 120 PeV. Right, the reconstruction of this muon track was particularly nice and well understood. Well, what I show here are different distribution of time residuals in different photomultipliers at several heights. Time residuals mean expected minus observed arrival time of photon hits at the camera. So the peak at 0 means that we understand exactly the propagation of our photons. They reach our cameras exactly when we expect them to do. And then there is a few less events at higher times that might be daughters of scattering. Then this muon track also presents an extremely rich detail, so extremely rich information. For instance, its light profile is consistent with at least 3 larger energy deposition along the track, which are the characteristical behavior expected for stochastic loss of high energy muons. Right, then we come to the physics related with this event. So first of all, the energy. And that's a very debated part because considering the KM3NeT exposure only, as I was saying before, this event hit our detector in a very small configuration. So with a very small exposure, short time and not large volume. That creates this extremely high point here in the spectral energy distribution because this event was exactly just not in line with, for instance, what IceCube was observing in the diffuse component. This is most likely due to a, let's say, serendipitous fluctuation that we observe this event as soon as switching on this small detector can occur. If this is the case, its height will diminish with time. But also we ran an analysis combining with the non-observation of such events by IceCube, and then with the upper limit that also Auger and IceCube at extreme high energy were able to place on neutrinos. So combining, having seen one event in total, 0 events from the other instruments, and then summing up the effective areas of all these instruments, the exposure of all these instruments, indeed the point is actually lowering down. Now what happens? I mean, the two measurements are different. This kind of approach of including all different instruments observing wasn't applied before, so that is why also we present what the point refers to when considering only KM3NeT. The real trouble comes with the origin, which we could not consistently frame up to now. So there is simply nothing behind, which is significantly the source of this event. So the coordinates of these events are here. Right ascension 94, declination minus 7.8, so it's slightly below the galactic plane. It's here, right? And I will present some searches that were run for a galactic counterpart, for an extragalactic counterpart, or most likely what remains are more exotic scenarios on cosmogenic origin. So, extragalactic counterpart first, because the first usual suspects when it comes to with astrophysical neutrino sources are AGN, so active galactic nuclei. So, a catalog search was run, inspecting several lists of plausible sources based on different criteria. So, radio sources, sources with high X-ray flux, sources high in Fermi, and then in the vicinity of the event, this is a zoom in the event position, 17 sources were inspected, and the 3 most significant sources was one source with a radio flare, coincident with the neutrino arrival time. The second one is a source with a rising trend in X-ray flux for a duration of 1 year around the event. And the third source is a source that shows a coincident gamma ray flare. However, none of these were conclusive. So we don't reach a statistical significance to ascribe the event to one of these sources. Given the energy of this event, this starts off to be very unlikely galactic because the energy is simply too high. However, we run a source searching for galactic counterparts. For instance, considering CO clouds, so indeed environments where a neutrino proton on target scattering could occur and a neutrino could be produced. We inspected known potential cosmic ray accelerator and the catalog of galactic gamma ray sources for FGL, HAWK, and LASO. Again, non-conclusive observation. So this event could not be related over the random probability to any of these classes of galactic sources. But again, given the energy, very unlikely anyway. And now what is left as a standard astrophysical scenario is that this event is actually a cosmogenic neutrino. Cosmogenic neutrino is a neutrino that comes off the scattering of a cosmic ray onto a CMB, so photon. So this creates a delta particle resonance and then issuing neutrino. So this is the natural horizon, the cutoff in energy that constitutes the natural horizon for ultra high energy cosmic rays. And if this were the case, this is, to my opinion, particularly interesting because then it means that with the exclusion of the cosmic neutrino background, a very, very futuristic science fiction measurement that we are still attempting to run, all the other neutrino components of the neutrino energy spectrum have been measured. So this is kind of nice on the one end. Right, and then, yes, and then finally, indeed, we also consider this event in order to constrain gamma ray burst parameters as well. So, to conclude, this event has no conclusive origin, is not a blazar, it does not appear to be galactic, is inconclusive as a gamma ray burst. and is also particularly high up and not aligned with diffuse points, so its cosmogenic origin also presents some stretch in the parameters. That leaves the window open for any other possible, more exotic scenario for its origin. For instance, any traceless transient, such as a primordial black hole evaporating, very convenient source, because it emits and then disappears, so you will never find it. Dark decay or something, like instead of owing its energy to extreme high energies to an astrophysical acceleration process, it might owe its energy to the very large mass of its progenitor, such a heavy dark matter particle. So again, very convenient source because it decays and vanishes. Or any other scenario that raises a lot of interest to this event. Then unfortunately, this event was not observed in real time. That means that this event was not transmitted to any network of prompt multi-messenger alert that would have helped a lot in constraining its possible, in reducing the random association with underlying sources, especially would have pointed gamma ray instruments to its coordinates by the time. So this was very unfortunate, and however, we do take part in multi-messenger networking. Of course, right now we are ready to transmit, we are ready, to receive, and we should be ready to transmit anytime soon in order that indeed KM3NeT can fully participate in this transmission of alerts between different instruments. And this is to say that apart this peculiar event, right, talking about multi-messenger, of course, the first to come, most wanted multi-messenger observation that we want to perform in neutrinos would be, of course, the correlation of neutrinos with gravitational waves, which we follow up. So we follow up online and offline events with the runs of Virgo LIGO, CAGRA, indeed, I should add, issuing alerts, and we follow up whether we have significant neutrinos. Of course, this search is made complicated by the rather poor angular resolution we do have for gravitational waves. So this is this kind of longer shapes, contours in sky maps. And to the time being, there was no observation convincing that neutrinos and gravitational waves are associated. Right. Then with KM3NeT, we will also address this other super interesting part of the energy spectrum, which is the galactic emission. Now, IceCube has very recently observed indeed neutrinos here in the very last panel of this figure from the galactic plane. Now, KM3NeT is a nice chance here because IceCube being at the geographical pole, so it's minus 90 south, the detector doesn't rotate, right? So it cannot perform an on-off analysis of sky coordinates. It has to rely on a benchmark model for galactic emission, such as CRA or CRINGE. So somehow KM3NeT, being at a random latitude, so it's a 36 degrees north for the cubic kilometer, we'll see like the galactic center and galactic ridge, nearby region, so rise and set. So in this way, it could observe with an on-off model-free or benchmark-free opportunity. And now this is not just, this is a steady emission supposed to be. So it's kind of a granted measurement that we wish to have in the very, very close future to come. Because it just does depend on size of detector volume and observation time. But it's not just a measurement per se, but it's a measurement which is puzzling, because if you think of any other, for instance, electromagnetic frequency, including gamma rays, right, the galactic center appears to be very, very bright. So our own galaxy outshines the rest. So we see our own galaxy before we can actually look behind. But with neutrinos, it happens on the other way around. So we caught diffuse neutrinos from extragalactic sources, much with stronger intensity than we start to now see the galaxy. Thank you. And so this hints at the idea that perhaps powerful accelerators operate in our galaxies that don't exist in our own. Oh. I apologize. Let's see. Why that? Mm-hmm. Maybe I can. Yeah. I'm really sorry about that. Let's see if this way it works. Oh, yeah. Yeah, so yeah, just flash the very last slides when it comes to other physics cases. So of course there are other types of cosmic neutrino sources, and they are one that is closer to what I personally do for a research topic is dark matter. Dark matter can actually annihilate to any standard model, many standard model particles, including neutrinos. So of course for catching dark matter signal, a triangulation is necessary between direct scattering and indirect searches. And what we actually aim of is to look at annihilation of dark matter. So given the very weak rates of annihilation, we have to go to cosmic environments once more in order to test regions where dark matter is supposed to accumulate to very high densities. And we do run searches for dark matter, especially targeting the center of our own Milky Way, because from our latitude, crossing the Earth, we see the southern sky. So we can actually test directly the arrival direction of neutrinos in the center of the galaxies, inputting the dark matter annihilation features and testing whether there is a cluster of events with the energy footprint that makes them daughter of a dark matter annihilation. And then this is the very last slides, also because I didn't mention anything at lower energies, that KM3NeT performs already more than 6 standard deviation measurement on neutrino, of the oscillation, flavor oscillation parameters for atmospheric neutrinos that we see using the muon neutrino disappearance channel. And this comes to the moment to 1.6 megatons of data. And that the main big measurement to come is an attempt to measure the neutrino mass ordering, using the fact that the matter resonance around 4 or 5 GeV will appear for will affect neutrinos if normal and antineutrinos if inverted ordering, and we have a chance of distinguishing these two cases. So I should conclude saying that there's a bright future ahead for neutrino telescopes, extraterrestrial neutrino sources, multi-messenger, but also the very big puzzle about these high-energy neutrinos still without source, and that we also can perform a measurement of flavor oscillation and very high thrill for the neutrino mass ordering. And also saying that this is a proliferation era for large volume neutrinos telescopes. As you will see, there is many in construction, but there is also plenty of open dilemmas. So as I like to remind, the most exciting sentence to hear in science is not everything is understood, eureka, but that's odd. So thank you.
Thank you, Rebecca. So while people prepare some questions, I'm going to object to the statement that the CMB was not predicted. The Gamov group, particularly the first paper was by Alfer and Hermann, had predicted it, and it was being sought at Princeton. There was a group preparing an experiment to detect it.
Thank you.
But the IBM, they were in telecommunications and so on. I don't know which group was this. Bell. It must have been the Bell Labs, right? One of these large collaborations in industry was setting up an antenna, and they came up with this without knowing it. They stumbled on it, right? It was serendipitous, but it was not unpredicted.
Okay. Thank you. Yes, I should correct myself.
Anyway, questions? Coming.
So, since 1987, the one and only neutrino supernova that we have detected yet. I am aware that other experiments, such as Dune, are aiming to detect this kind of things, and they are developing new technology to do this. So will KM3NeT be able to have the sensitivity to detect these kinds of...
Yes, thank you. Yeah, I neglect to mention this due to time, but yes, indeed, we also have a supernova neutrino program. So in our energy window, I was just flashing GeV to PeV, but around the MEV, we expect neutrinos from supernova. But this kind of analysis does not rely on our standard data taking modes or reconstruction. It relies on single optical modules. So what we wish to measure is the global enhancement in rate that interests more optical module at the same time. So this is our trigger. So this is our signal would look like. So we have it ready, and this is actually also participating in this multi-messenger alerting system, because neutrinos are precursor. So it's fundamental to know when neutrino flash, everybody should look in this. And I should also mention that in this rate of 1 per century, we might be expecting it soon. Yeah.
Okay, so I had a question about the cross-section. You have a neutrino, one event at a huge energy, and up there the cross-section is not that small anymore. So 300 kilometers of water equivalent would make it opaque, right? It's very unlikely that such a, what was it, 200 peta-electron volts, something like that? That should be stopped by 100 kilometers of rock. So you got very lucky. Let's call it El Gordo.
Yeah.
How is this possible?
This is undoubtful. Yeah, this is undoubtful. So to determine our energy of our mu1, we strongly rely on Monte Carlo simulation, and the cross section is inside that. So we strongly rely. So we have no other way. So what we can tell for sure is that the signal is there, and what we can also tell for sure is it's definitely not a mu1. Okay. Because a mu1 would be stopped in ignore. So for however unlikely,
okay. It has to
the alternative hypothesis might be the truth, because...
Should you not be seeing already neutrinos at the glacial resonance? If you can see at 200 peta.
Which we haven't, indeed.
You haven't yet?
No. IceCube has a candidate for glacial, but we have not. But this is actually that we don't have glacial events is kind of expected in trend with our volume. We're much smaller. This case must have been just simply a lucky transient.
Okay. Questions from the public? A graduate student question? Well, we've had one. So I have a last one. I see that someone's hungry. Okay, maybe. I'll yield.
Hi. So for extragalactic sources such as blazars, to exclude them as plausible sources, is the non-observation of flares in Fermi-Lat energy range like a mandatory, how important is that to exclude them? Also, you mentioned that you couldn't point with the other gamma ray instruments during the observation of the neutrino. So would it be useful to look at the region a few days after to look for any radio observations or radio flares?
Yeah. Okay, so 2 questions, here are the 2 answers. First of all, to exclude the blazar origin for this event, the strategy to follow is we don't rely on the absence of flares. Indeed, we didn't even observe gamma rays, instruments didn't even observe at that time. And as I was mentioning, it can as well be that the source emits both neutrinos and gammas, and just gammas go absorbed. So the absence of a gamma ray flare is not conclusive. Maybe the way I formulated can be tricky. So to exclude the blazar origin of this event, I should have said that we are not still meeting the necessary significance to prove it as the unique possibility. So we're still affected by random association probability. Why that? Because in fact, the error we issued this event with is actually a 3 degree 1.5 to 3 degrees, 68 to 99% confinement region. And now 3 degrees is huge. There's plenty of stuff in 3 degrees. So 3 degrees looks little to you, but is really a large number for astronomers. Might be look little. So in 3 degrees, the chance of a random association is so high that you cannot conclusively state if you find an object, you surely find an object behind. You just cannot say for sure it's the source, simply because of that. So your other question is correct. Yes, the flare duration is completely arbitrary as we see. There are flares of a few minutes, flares of a year, flares of many days or months. So it would have made sense indeed to look for archival data even 2 days after or so, but this event comes with a latency of good 2 years, so a year and a half. So for sure there was as possible search back for archival data of other messenger wavelengths, but to the time being, it's not that we can exclude it. It's still in the air, but we cannot frame it for sure. So we don't have the 5 sigma significance to say this source is the mother of this neutrino and no other possibilities. So it cannot be a random association. Maybe this formulates it a bit better. Yeah.
Beautiful timing. Beautiful timing. Thank you everybody for coming. Let's thank the speaker for taking the train over to Madrid.
Yeah.
And next month we go back to theory, talk on the strong interactions. The poster is already around. Thank you.